Regulation process. Again, if you're not down with the theory, how do the arrows go in this one? They're inverse. And what do I mean by the inverse? It's still the relationship to line, load, BCD. That's what I mean. Oh, arrows are inverse this time. So the first circuit relies on the voltage drop to regulate. You understand what I mean?
Yes, sir.
The voltage. This circuit, the way the transistor configured, relies upon the branch currents to help regulate the output. Can't figure that out yet. Line increases. Here we go. We're still trying to maintain nearly constant output, yes?
Yes, sir.
And what is that nearly constant output?
3 volts.
I'm calling it a 3-volt zener this time.
3.6.
So now, because I made it up, doesn't matter. 3.6 volts, we're trying to maintain nearly constant. Got it. What do we always need to remember when the line increases or decreases? I total is affected right now, isn't it?
Yes,
Yes,
sir.
sir.
It is. So just imagine, hey, line increases the whole circuit. That current is going to be felt to increase. But at the same time, we've got R3 limiting the current to the zener, maintain that relatively constant, because VCR1 plus this equals the output, doesn't it?
Yes, sir.
Every one of these branches, except for this branch, this branch, and this branch have the same voltage, don't they?
Yes, sir.
They should, because that's how it works. 3.6 volts here, 3.6, and 3.6 at the load. Because what's common in parallel?
Voltage.
Nobody said series this time. Good job. So what sets the output voltage? Doesn't it?
Yes, sir.
Okay. So the zener branch current is relatively constant, isn't it?
Yes, sir.
And the big change happens here to the load. So if I increase the line, do I want excess current or the increased current to take that bigger current times same fixed value resistance and increase the voltage drop?
No, sir.
Do I?
No, sir.
No! Coin, look. Just imagine, I total increase. Why? Because we're here. We're here. We're increasing the line. This is all current. This increase could potentially cause the output voltage to increase, couldn't it? That's his own law and stuff. So if I have more branch current, just look at this. Look at that branch already where the transistor's at. What do you think's going to happen here? The conduction of the transistor. Okay. What about R4? What's the voltage drop of R4 going to do? Because that's why I wrote this, because R4 is special. Do I have more current in this branch? Okay, VR4 is going to increase. If I have more current being applied to that transistor, isn't that 100% of the current?
Yes.
Isn't that 100% of the current? Isn't that 100% of current? Am I increasing current?
Yes,
Yes, sir.
Can I do this?
yes, sir.
Can I do this?
Yes, sir.
This, load line characteristics. If R4 goes up, VCE has to decrease, because guess what? This has to Kirchhoff out and match what this is, so this matches. If VR4 goes up, VCE has to go down. It's got to compensate, because I don't want that to increase, do I?
No,
No, sir.
That's what R4's job is this time in this circuit. It's voltage drop. More current. It's a resistor, isn't it?
Yes,
Yes,
sir.
sir.
It's a resistor. If there's more current, its voltage drop is going to get bigger. It's a resistor. That's how a resistor is. That's how it works. That's Ohm's law. Didn't we use resistors when we started out?
Yes,
You know Ohm's laws? You can understand how it works? Yes.
Yes, sir.
That's the compensation. This branch right here is going to remain relatively constant, isn't it?
Yes, sir.
Here's the kicker. This is still a regulating element. There's more current transistor. Hey, emitter's 100% of current, right? If I add more to that 100%, isn't that going to make the transistor conduct more? This whole branch right here. Hey, isn't the potential at the top and the bottom? So isn't R4 going to feel the increase too?
Yes, sir.
Yes, that's what I'm trying to tell you. What about decreasing the line? Yeah, it's going to be opposite. Now I don't want less voltage. I need more. So, if I take these arrows and point them down, now the transistor is going to conduct how? Yeah. Should be less. What's VR4 going to do? Yeah, less current times a fixed value resistor means its voltage drop is less. If VR4 decreases, VCE here has to do what?
Increase.
To compensate and equal that 3.6 volts nearly constant. See what's going on here?
Yes.
What's additive in series?
Current.
Really?
Voltage.
Voltage is additive in series. So if how many elements are in this series branch? What do we have? We got R4. What else is in that branch? Q1. How many components are in that branch? 2. If VR4 goes down, and I'm trying to equal 3.6, what does the VCE have to do to equal?
Increase.
Everybody understand that?
Yes,
Yes,
That's
sir.
what's called like Kirchhoff's voltage law in a series circuit.
Yes, sir.
Yes. See how simple I'm trying to make it for you?
Yes, sir.
I'm trying to make it simple. What about the load side?
It's the same way, sir.
That's basically the same thing. But here we can really use this formula to help us out. What did I say about the Zener branch? It remains relatively what?
Constant.
This R3, it's a small resistor too. It's like 120 ohms. It can handle a significant amount of current. But again, the Zener voltage is going to remain relatively constant over a what range of currents? A wide range of currents. It's how a Zener works. So we can effectively say, since the formula V out equals VCR 1 plus 4 voltage, isn't that that? Isn't it that?
Yes, sir.
What's common in parallel?
Voltage.
See? Everybody understand? Are we getting it?
Yes, sir.
Heckman!
Sir.
Are you getting it?
Yes, sir.
All right. Load. That's where we're at now. Increases. Well, we can come over here in this Zener branch. Can I do an arrow point to the right?
Yes, sir.
Relatively constant. Hey, we can do that. If the load resistance increases, immediately think about that branch current. What's it going to do?
Decrease.
Does that make sense?
Yes, sir.
Can I do this?
Yes.
So if that branch decreases, that's relatively constant. What the current in this branch, where does that current that's not needed by the decreased load go? It's got to go be felt elsewhere in the circuit. It doesn't disappear. So that must mean, hello, does that make sense?
Yes, sir.
So therefore, I can come to my arrow analysis. Hey, load current decrease. Oh, we're doing a load increase. Transistor, oh, it's going to receive that extra current that's not needed by the load. So I can do like this, can't I?
Yes, sir.
Yeah, what's VR4 going to do?
Increase, sir.
Yeah, there's more branch current. VCE,
Yeah, decrease, sir.
because if VR4 goes up, VCE naturally, to equal that 3.6 nearly constant, it's got to do what?
Decrease, sir.
Amazing. Load decreases. It's opposite. If I put a smaller load in here, smaller load, it's not much, it's less opposition to current, right?
Yes, sir.
So naturally, where's the extra electrons that's like floating around? Hey, let's go over here. Now what's going to happen?
Yes, sir.
So isn't the load the load current going to increase
Yes, sir.
due to a decrease in load resistance? Yes. Guess what we can do now? Oh, well, if it goes up, what does the branch current here have to do? Hey, guess what? Now we're dealing with Kirchhoff's current law, aren't we?
Yes,
Yes, sir.
Hello? Total current. has to stay the same, doesn't it?
Yes, sir.
So now there's where the compensation takes place when the load changes. Less transistor current. Hey, you can come over here, conduct less. Voltage drop R4.
Decreases.
Since VR4 that goes down, VCE has to. So I need that 3.6 volts back. Amazing. There it is. Now, since day 3 or 4, whenever we started doing the regulators, from that day to now, does this stuff make a hell of a lot more sense?
Yes, sir.
Now, you might not be able to go through the rigmarole that I do to explain all this stuff, but if you have at least yeah, I get it. It's the voltages here, it's the branch currents here, is where the compensation takes place. If you got that, you're going to be okay. If you're not down with theory, guess what?
Screwed.
Well, maybe. Know the narrow analysis, but I just explained, and this time we got a tape to prove it. I just explained both of these in its entirety, the best that I can, as easy as I can, to help you and make you understand. That's how these things work. And don't forget, you guys did the labs, hopefully. I know you did. Well, I don't know if you did them right. Because some of you like to, but what do I always say? If you don't understand what's going on in the lab, raise your hand and come over there. How we doing?
Good.
Row number 1, how we doing?
Great, sir.
All right. Row number 2.
Outstanding, sir.
Row number 4.
Good, sir.
How you doing, Brown?
Fuzzy, sir.
I'm going to take a break. Take a break right now in a second. Okay. We good down here?
Rah.
Fuzzy.
Ah.
All right.
Good.
Oh, we're just going to start saying rah now? Okay.
No, sir.
Keep reminding me of Lady Gaga. Rah, 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 rah. We are going to take a break. Come back, we're going to wrap it up.